Another one is using the wrong lengths for our strings, the wrong scales, the wrong precisions, just assuming that every string is a varchar 2 4000. This doesn't happen with every client API, but you could definitely run into cases where if you just define everything as a really large character string, a varchar 2 4000, versus right-sizing it, you could come up with some really large memory allocations. Some JDBC drivers do this, some do not. You could switch one day from one JDBC driver to another and all of a sudden find out that your memory use explodes. But just think about it. If everything was stored as a varchar 2 4000 and you had 10 columns, whose on average the width would have been 40 characters apiece, so some of them are really 80 characters, some are 10 characters. If you use a varchar 2 4000 and you have 10 columns, a client might have to set up a fetch buffer of 40,000 bytes for that. But we really don't just fetch a row at a time. Hopefully we don't fetch a row at a time. Hopefully we fetch maybe 100 rows at a time. So that's going to be 100 times 40,000 or 4 million bytes. That's 4 megabytes. That's nothing. But in our application, we have, say, 25 cursors open at a time. Now that's starting to add up. That's 100 megabytes. But we have a connection pool with 30 connections. That's all of a sudden 3 gigabytes of fetch buffers. This can affect client memory allocation. It will affect reporting tools. Think about a reporting tool. If everything's a varchar 2 4000, you're going to get really wide columns out of your initial layout. You're going to spend a lot of time fighting the data in the database. Additionally, if you make every column a varchar 2 4000, the only thing I can guarantee you is someday you'll have somebody with a last name that is 4,000 characters long, right? Because you don't have the edit on there to put sanity checks on the information. Constraints are important. So getting beyond just data types, constraints are facts. They tell the optimizer, they tell the database, they tell you and me about the data. They contain more information. They convey this information to the optimizer. Most importantly, the presence or lack of constraints open up or remove access paths that would not otherwise be available. Here are a couple of examples, and this is not the finite set of examples. These are just a few high-level ones. Check constraints, simple check constraints that tell us about the data. They constrain what values can go into certain attributes or sets of attributes. I'm going to create a table. It only stores information about tables and views. I'm not only going to put this in the where clause when I build this, I'm going to assert this as a check constraint. This is read-only information. Maybe I never modify this. But when I load it, I know that it only has tables and views. So I'm going to tell the optimizer that information. I've got another table. All it has are synonyms and procedures inside of it. I'm going to tell the optimizer again that fact. Think of a data warehouse or reporting system where you're not using partitioning. Instead of my example with table and view and synonym and procedure, pretend that was a year column. Everything I load into table 1 is year 2006 data. Everything I load into table T2 is year 2007 data, and so on. You know it's year 2007 data. In fact, you probably would even just name the table T_2007 to represent this holds year 2007 data. Tell the database that fact as well. Because in your reporting system, you're probably creating a view that your end users are going to use. So here I take the view of the two tables and I union all that data together, gather statistics, and I go to run a query. If I look at my query, I never said that in my query. The query's at the top. I just said object type equals table. I can see that filter applied to both of the tables. Where did this filter null is not null come from? The optimizer rewrote my query. The optimizer stuck that in. When this plan is executed, this filter will happen first, meaning that full scan never happens at all. We don't go down there. We just pruned that table out of the explain plan altogether. It still appears there, but we'll never actually touch it. If you turn on SQL Trace and run this, we can verify that, because in the TK Prof report, we'll be able to see that 0 rows came out of that full scan down there at the bottom, but the number of consistent reads, the IOs we performed against the table, was 0. We never hit it because this filter prevented us from going down this path. So we only ever full scanned the table T1. This is just like partition elimination, but you can do this with a union all view. If I drop those constraints and I rerun the query, the row source operation from TK-Prof at first looks pretty similar. There were 2 full scans. There's still 0 rows coming out of it, but notice that I'm now doing 408 IOs against the table. We had to actually full scan it because the database no longer knows that the information we require can only exist in table T1. It's not able to do this partition elimination. This is actually called view partition elimination, and it's been in the database since version 7.3. Not null. I wish that the default for a new column in a table was to be not null, because most of our attributes are, in fact, not null. It's very rare to have an actual attribute that allows nulls in many cases. Everybody has a first name. Everybody, well, I guess except for Madonna and Cher, have a last name, right? But I bet you they too have a last name. But we have addresses and things like that. These fields, most of the times, are mandatory. And if the default was not null, I have a feeling that not null constraints, which would be the default, would be more widespread. More of our attributes would have it. Create a table T, select from all objects. Create an index on object type. Gather statistics on this table. Then ask the simple question, how many rows are in the table? Table access full. Why didn't it use my index? My index is obviously much smaller than my table, and we know that every object has an object type. You know it, I know it, database does not know it yet. So when we ask to count everything in there, we can't use that index because that index is on a column that may contain nulls. It doesn't, but the optimizer doesn't know that. The optimizer has to check every row. And when we create an index in Oracle, if the index key is entirely null, we don't place it into the index structure. So if one of those rows actually had object type null, it would not be in the index in this case. We can't use the index to count the rows. Alter the table, modify that column to be not null, select the count, we immediately change the query plan. It's going to be an index fast full scan. It's going to use the index as a small skinny version of the table and just count how many leaf entries that it sees inside of that index. So adding that null, not null constraint gave us an access path that did not exist before. Here's another way to do that. What if object type did permit nulls? One way to get an index on a nullable set of items is to add something not null to the end of the index. And this is just sort of a trick. If object type was nullable, but we wanted to be able to use an index on object type for a lot more stuff, including queries like where object type is null, well, all I need to do is add one not null attribute to the index. And here I'm doing that. I'm adding the number 0, the expression 0. 0 is not null. So by having this index, even though that object type allows nulls now, when we do the count star, we can still use that index. Because 0 is never null, we know that every row is now in the index. Here's another example. Create a table T. We're going to make 1 out of every 1,000 elements in this table have a null value. Most of the rows, 999 out of 1,000, have a not null value for this new column that I've added, object type.